vector calculus is a little bit advanced form of normal calculus, and even though although this part this is not in the syllabus of any competitive exam, vector calculus, but to understand some theorems like Gauss's theorem, Ampere's theorem, so you must have idea about vector calculus. So we will just superficially discuss about vector calculus. We will not go in the deep, because these concepts you will learn in your higher mathematics in engineering or in graduation or post graduation. So at that level these concepts are discussed in detail, but at this level, for competitive exam purpose, for higher secondary purpose, you need not to go in detail of vector calculus. We will just discuss it superficially to give you a background, to give you the idea about how this vector calculus is used indirectly or directly in higher secondary level, like in Gauss's theorem and Ampere's theorem, which I have discussed. So to understand Gauss's theorem, you can directly read the formula, and Ampere's theorem you can directly read the formula and solve the problem. But to understand the derivation of Gauss's theorem, derivation of Ampere's theorem, you will have better understanding after understanding these derivations. To know the derivation and to understand these theorems deeply, you must have idea of vector calculus. That's why we are discussing vector calculus here. So vector calculus, first of all, we will discuss some basic terminologies which are used in vector calculus. Basic terminologies, basic terms, they are used frequently. So before going in detail, we will understand, we will discuss these basic terminologies of vector calculus. So first you will hear about field. So from the start of vector calculus, you will listen, you will read the term field. So field is how the field is defined in vector calculus. In simple term, field is nothing but it's a physical quantity spread in space or represented in space by a scalar or vector function. It's a physical quantity. It can be a scalar field or it can be a vector field. Scalar field is given by symbol of function, which we have discussed in terms of x, y, z. So at point x, y, z, you can put the values of point in the function and find the scalar value of function. That is called scalar field. For example, you have discussed various functions. Let f x, y, z is equal to x square plus y square plus z by 2. So this is a function, simple function in three-dimensional space. So at any point, let 1, 2, 4. So let a physical quantity in space x, y, z direction. This is x direction, this is y direction, this is z direction. Sorry, this is x direction, and we will represent z direction here and y direction. So in this three-dimensional space, this scalar physical quantity, it can be any physical quantity, like for example density of material. Let us assume there is some material. In this material, let the density is changing at different points, and the density at general point x, y, z is given by this function. So this is a scalar function. So let, for example, at point 1, 2, 4, the value of scalar function is 1 square plus 2 square plus 4 by 1 plus 4 plus 2 equal to 7. So this is a scalar function represented scalar field, for example density, for example other physical quantities like temperature is given by particular function represented by this function. So all quantities we know which need not all quantities which don't need direction to be represented in a space, they are all scalar quantities. So like density, temperature, time, speed, they are all scalar quantities. So scalar quantity in space is represented by this function. So this is called a scalar field, and the value of field, that is value of physical quantity. Field means physical quantity. Value of scalar field is given by this function at point x, y, z. At this specific point, you can find value of this scalar field as 7. It can be temperature, degree Kelvin, it can be density, it can be any other scalar quantity. So this is the way we represent scalar functions, scalar fields. Similarly, second terminology is vector field. Vector field is similar to this scalar field. In vector field representation, we represent a vector quantity, physical quantity, which nature is vector form. So let us, for example, at point x, y, z, vector field like force, like velocity, so like magnetic field, gravitational field, electric field, these are all, we know, vector quantities. So these vector quantities, physical vector quantities, are represented in three-dimensional space. For example, fx, y, z is x square I plus y by 3 j plus zq k, where I, j, k, h, as we have discussed in vector chapter, in vector discussion, I, j, k are unit vectors in x, y and z directions. So you can see this is a vector field at point x, y, z. At point x, y, z, vector field, it can be a magnetic field, it can be an electric field, it can be gravitational field. So these are all vector fields, vector physical quantities. So representation of these vector quantities, physical quantities, which are vector in vector form, is given by this function fx, y, z. This is a vector function and it is represented in terms of I, j, k. So what does it mean actually? So let this is giving a gravitational force. Gravitational force. This function is representing gravitational field. So at point 2, 4, 6, just for example, I have taken this point. At this point, the value of gravitational field can be calculated from this function. So just put 2 square I plus y is 4 by 3 j z 6 q k. This you have got absolute vector. This is the field at point 2, 4, 6. So what does it mean actually? The value of gravitational field, at point 2, 4, 6. Let this is point This is given point 2, 4, 6. So at this point we have found the value of the gravitational field equal to 4I plus 4 by 3J plus 6Q. Just for example, we have taken it. So this is a vector quantity. So this vector you can assume here the value of this vector, the tail of the vector, you can start from this point and you can draw the vector. Let this vector is represented by 4I plus 4 by 3J plus 6Q K. This vector is gravitational, representing a gravitational field at point 2, 4, 6. This gravitational field is represented by this vector function at point general point x, y, z. So this vector you can represent at point 2, 4, 6 having tail starting from this point. Just remember, tail of the vector should start from this point and rest magnitude and direction of the vector will be as per its property. So this is 4I plus 4J plus 6Q. Okay. As we have already discussed that vectors are free. So this vector can be represented position anywhere. Here also you can represent 4I. This vector you can also represent 4I plus 4 by 3J plus 6QK. So there are number of vectors representing this vector, specific vector. There will be infinite representation of these vectors at different places. But as this vector is specific to this point, so this is a convention. This is just a convention. It is not a mandatory or compulsion. This is just a convention that this vector you just represent tail starting from this point and direction and length as per the property of this vector. Whereas this vector can be represented anywhere in three-dimensional space. So that is the definition of field. In short, field is nothing but a physical quantity. Field is a physical quantity represented by a function in three-dimensional space. So we use a function. It can represent a vector field. It can represent a scalar field. Based on which quantity, physical quantity, we want to represent in three-dimensional space. So you will frequently come across this terminology field in vector calculus. Just for another example, we know electric field. This is electric field. Electric field at a distance. This is let charge. Let this is charge plus Q placed at origin of this three-dimensional coordinate system at distance r. At distance r, the value of electric field is 1 by 4 pi epsilon 0 Q by r square. That is Coulomb's law. You know this is Coulomb's law. So this field, this charge plus Q charge, this plus Q charge will generate electric field, and this field can be represented by a function. So we will just, for example, we will represent this electric field generated by this plus Q charge in terms of function, how this electric field is represented in terms of function. So that is very simple. Let this point is x comma y comma z, point P. So this is the general point P, x comma y comma z. So we will find electric field function for a general point. This distance r, you know, simple formula, r is under root x square plus y square plus z square. So E can be written as 1 by 4 pi epsilon. Here E is a vector, but we have just written the modulus, the magnitude of E. So the function will include both magnitude as well as direction. 1 pi epsilon 0 q by x square plus y square plus z square. That is magnitude of electric field at point x comma y comma z. Now we have to find direction. So direction, you can see simply, you can see direction of this field is out. Let this point is O and this line is OP. So direction of field will be towards OP. The direction will be towards vector OP outward, in the direction of vector OP. That is O and that is P. So position vector of P, OP is xi plus yj plus zk. So that simple representation we have discussed in in the chapter of vectors. So position vector of P, that is OP, can be represented as xi, yj, zk. And the direction of this force, electric field, is also towards vector OP. We know Coulomb's law. From Coulomb's law, electric field is radial. It will be radial. That is line joining OP and outward direction. Sorry. So we have found modulus, magnitude of vector. Now we want to find direction. So unit vector in the direction of vector OP is unit vector along OP. Unit vector along OP is vector OP by modulus of OP, that we have discussed. That is xi plus yj plus zk divided by under root x square plus y square plus z square. So this is unit vector along OP. So now vector E is also in the direction of OP. So we can say vector E is equal to mod of vector E into, let this unit vector is OP cap. Just cap we are using to represent it as a unit vector. It is in the direction of unit vector OP. So vector E can be written as, so this is unit vector and this is mod of vector. This is mod of vector, that is mod of E, and this is unit vector, that is vector OP. This mod is 1 by 4 pi epsilon 0 q by x square plus y square plus z square into this vector, unit vector, that is xi plus yj plus zk divided by under root x square plus y square plus z square. So this vector E, vector field E, that is electric field, it's a vector field due to this point source plus Q. at point general point P is given by 1 by 4 pi epsilon 0 q by x square plus y square plus z square power 3 by 2. This x square plus y square plus z square plus into under root x square. This is the modulus and is in the direction xi plus yj plus zk. That part. So this vector field due to this point source plus q, that is electric field, which we call in general language we call it electric field. So this field is represented as at point P, that is general point x comma y comma z. This field is represented as 1 by 4 pi epsilon 0 q by x square plus y square plus z square power 3 by 2, and this vector xi, this is I, this is I, xi plus yj plus zk. So that is the way we will represent electric field in three-dimensional space. So this is how we talk and how we interpret field, term field discussed in vector calculus. So field is nothing but a vector field or scalar field, that is a physical quantity represented in three-dimensional space with the help of a function. That function can represent a vector field or a scalar field. So this example, simple example we have taken to represent a field produced by plus q charge in three-dimensional space. Second term you will come across is gradient. Operation of gradient. So operation of gradient is analogous to derivative in normal calculus. In normal calculus we find derivative or differentiate a given function. So that is the derivative. In vector calculus we call it gradient, that is analogous to derivative. Or derivative is also gradient, because gradient is rate of change. This operator is called del. This is all the name of this. This is actually a vector operator, and it is represented as del x I plus del y j plus del z k. So this operator is called del. This operator is represented by this expression. It's a vector operator because it involves I, j, k. When we use this operator for a vector function, we will use this operator for vector function and for scalar function in different ways. Then the operation is named as per the method of using this operator. So this operator is called del, and classical name of this operator is nabla. So nabla or del, whatever you can choose, you can call this operator del, nabla, and when this operator, so we will just have property of this operator, another property of this operator, del dot del. This is called del square. This is called del square. So del dot del is del x I plus del y j plus del z k dot del x I del del y j del del z k. So this dot product, we have discussed dot product in vector chapter. So this will be second derivative in terms of x, second derivative in terms of y, plus second derivative in terms of z. This is del square. This del square is also called Laplacian operator. So you need not to know much about Laplacian. We have just mentioned the dot product of this del dot del is del square, and this del square is called Laplacian, and del square is represented as del second degree derivative in terms of x plus in terms of y plus in terms of z. So this del operator is used in different ways in vector calculus, and it generates different physical quantities. Gradient operation, when this del operator, we have mentioned gradient, this actually operation of del with a function, scalar function, is called gradient of that function. This operator is del or nabla, represented by this expression, and gradient operation, let there is a function fx comma y comma, this is a scalar function, just remember, scalar function is, we have discussed, it will be a simple function in three-dimensional space for a general point like density, temperature, speed, etc. So gradient of a function, this is called gradient of function x comma y comma z. So what will be gradient of a function? So just use expression this for del operator. So gradient, this is also called grad. In short, it is called grad. Grad f x comma y comma z is equal to del x f x comma y comma z I plus del y f x comma y comma z j plus del z f x comma y comma z k. Grad of a scalar function. Gradient is always found for a scalar function. Just remember it. Please, this is a scalar function. Grad of this scalar function will be partial derivative of x by z I, partial derivative of x by z with respect to y into j, partial derivative of x by z with respect to z into k. So you can see this was a scalar function. When we used this operator, del operator, as a gradient to find the gradient of this function, we got a scalar field. This will when you will solve this will be a vector field. From scalar field we have found a vector field. So we can say gradient of a scalar function is a vector field. We will just use an example. We will go through an example. So just simple example, let there is a scalar function x square plus 2y plus z cube. This is a scalar function. Let this is a temperature in at point x comma y comma z. At point x comma y comma Z. This is temperature or any other scalar quantity. Whatever scalar quantity you can think it can represent. So this is, you just remember this is a scalar function. So we want to find grade of this scalar function fx comma y comma z. It will be, it can be written as del f x comma y comma z. When you, this is called grad, that is gradient of x function, and this del operator is used to find gradient of this function. So this is also called grad. So how this expression will be expanded? It can be written as I del y j del z k into function x comma y comma z. That is the definition of grad. Sorry, del operator del. This is a vector operator. So in general terminology, general writing, we don't use this vector symbol. We just write like this. So this is the expression for del, and this is function. So this is grade of fx y z function. So it will be del x fx comma y comma z I, that is partial differentiation of function with respect to x plus partial differentiation of function with respect to y into j plus partial differentiation of function with respect to z into k. Now put the value of function in this expression. So this is partial differentiation with respect to x. So these two terms will be constant. Y and z are constant for partial differentiation with respect to x. So it will be 2x I plus partial differentiation with respect to y. So x and z will be constant. This is 2j plus partial differentiation with respect to z, that is x and y will be constant. This is 3z square k. So this is grad f. This can be written as grad f x y. So we have got a vector function, vector field. By gradient, finding gradient of a scalar function, that was a scalar function in three-dimensional space. When we use this operator gradient, this del operator, to find gradient, so we have differentiated this function with respect to x, y, z partially, and I, j, k. The term I, j, k are used in this del operator, which converts scalar function into vector function. 2x into I plus 2j plus 3z square k. This is a vector function. So let's find at point 4, 3, 2. So we will find gradient at this point. So at general point, gradient is given by 2x I 2j 3z square k. So this is gradient of f at point x comma y comma z, general point. So gradient at point 4 3 2 will be 2 into 4 I plus 2 j plus 3z square 4 12 k, that is 8i plus 2j plus 12 k. That is gradient of function at point 4, 3, 2. At this point, gradient of this function is 8i2j plus 12k, and this is a vector. You can represent this vector in three-dimensional space. So, in short, gradient is operation analogous to derivative, finding derivative in normal calculus, because here we differentiate the given function with respect to x, y, z partially, and we get a vector function from scalar function. So only two important properties of gradient: it's analogous to derivative, and it generates a vector field from a scalar function. It converts a scalar function into vector function. It converts a scalar field into vector field. That is the property of gradient. Potential energy, that is gravitational potential energy or electrostatic potential energy. So those functions which you have studied are scalar functions. When you will find gradient of those functions, gradient of this function, you will find a vector function, and the vector function is original force. For example, gradient of gravitational potential energy will give you gravitational force function, and gradient of electrostatic potential energy will give you electric field. So that is the use of gradient function. We will just discuss physical use of gradient, physical application of gradient, where the potential energy, there is a mass m. This is mass m at point r, distance r. So let us assume that this point mass m is kept at the origin. So we know from Newton's law the potential energy of unit mass. Potential energy of unit mass at point P is G m by r. There is a simple formula of potential energy, G m by r. So we will find gradient of potential energy, and we will show that gradient of potential energy is gravitational field. So this potential energy at point P is given by this expression. Function point P coordinate are x, y, z. So this can be written as minus G m by under root x square plus y square plus z square u. Now we will find grad of this. Grad of u is equal to del u. Just use the expression of del. You can see minus Gm. This is potential energy for a unit mass. Due to this concentrated mass, there will be a gravitational field. For a unit mass placed at this point, 1 kilogram left, 1 kilogram. Unit mass, potential energy is given by this expression. So, gradient of this potential energy is minus Gm del x and 1 by under root x square plus y square plus z square into I plus del y under root x square plus y square plus z square into j plus del z 1 by under root x square plus y square plus z square k. This is grad u. gradient of potential energy function. So we will find it minus gm. Now partial derivative of under root x square plus y square plus z square is minus 1 by 2 x square plus y square plus z square minus 3 by 2 power minus 3 by 2 into 2x I. That was partial differentiation with respect to x for this function. Similarly, minus 1 by 2 under root x square plus y square plus z square, x square plus y square plus z square per power minus 3 by 2 into 2y j plus minus 1 by 2 x square plus y square plus z square power minus 3 by 2 2z k. So we have partially differentiated this potential energy function. We got this minus gm. This minus is everywhere, so you common take this minus out, so this will be plus 1 by 2 everywhere. This 1 by 2 cut it, this 1 by 2, this 1 by 2. So this function will be reduced to x by x square plus y square plus z square power 3 by 2 I plus y by x square plus y square plus z square power 3 by 2 j plus z by x square plus y square plus z square power 3 by 2 k. This is grade u, gradient of potential energy. This can be written as gm by x square plus y square plus z square. It can be written as xy under root x square plus y square plus z square I plus y by under root x square plus y square plus z square j plus z by under root x square plus y square plus z square k. X square plus y square plus z square is nothing but distance r from origin end point. We can write it r square, and this vector is nothing but vector OP by mod of vector OP. This vector is xy under root x square plus y square plus z square I plus y by under root y square plus. This is unit vector of position vector in the direction of vector p. If you will find unit vector in the direction of p, that is unit vector in the direction of vector OP, that is the unit vector, because this under root x square plus y square plus z square is modulus of this vector, and xi yj zk is position vector OP. So I will just write vector OP is equal to xi plus yj plus zk, because point coordinates of p are x, y, z. Vector OP is this. So unit vector along OP is equal to vector OP by mod of vector OP, and this is xi plus yj plus zk divided by under root x square plus y square plus z square. That is same thing. You can write it like this: gm by r square xi plus yj plus zk divided by under root x square plus y square plus z square. So this is unit vector. This can be written like this. So this is gm by r square, and unit vector, I will write unit vector along OP as using cap. So that is G. You know, by Newton's gravitational law, gravitational acceleration is given by this expression. So we have found here that when you find gradient of potential energy, we got gravitational acceleration expression. We got a vector field. This is a vector field, vector OP. This is vector OP. This is vector, unit vector OP. So this G is a gravitational acceleration, is a vector field which has been derived by finding gradient of potential energy due to this mass m at point P. When you find gradient of potential energy field, that is scalar field, you find gravitational field, you find expression of gravitational field which is vector field. So this is another example that gradient of a scalar field is always a vector field. So here we found this vector field, that is gravitational field G, by finding gradient of potential energy field, that is scalar. Second is divergence. This is written like this. So we have I have earlier told you that this del operator is used in different ways to get different type of operations like gradient, divergence and curl. Third will be curl. All these three operations are done with the help of del operator. It is used differently. So we have discussed how del operator is used to find gradient of a function. Now we will discuss how del operator is used to find divergence of a function, and then we will discuss physical interpretation of divergence. What is divergence? So we know del is a vector operator, del x I, del y j, del z k. Divergence, unlike gradient we have found for a scalar function, whereas divergence is found for a vector function. Divergence is found for a vector function. So divergence, it is written like this, of a function x, y, z. This is a vector function, is equal to del dot x, y, z. Because here function is a vector function, we know dot of, this is dot product of del and a vector function. Simple, this is a dot product of del and a vector function. That is called divergence. So we know for dot product we must have a vector function. Dot product cannot be found for a scalar function. So dot product of del and vector field is called divergence of a vector field. Simple example of divergence. Let there is a function, vector function f(x, y, z) is equal to 3x I 4y square j plus z square k. We have just arbitrarily chosen a vector field. Now we will find divergence of this vector field x, y, z. This is del dot function, vector function. This can be written as del del x I plus del del y j plus del del z k. That is the definition of del dot this function. That is, this function is represented as 3xi 4y square j plus z square k. So you have to find the dot product. So I, you state I dot I is 1 and the dot product of I with these two components will be 0. So that we have discussed the dot product in vector chapter. So this will be partial derivative with respect to x for component of I 3x plus partial derivative with respect to y for component of y 4y plus partial derivative with respect to z component of k, that is z square. So when we find dot product, this has converted into scalar function. Now this is 3 plus 4 plus 2 z equal to 2z plus 7. So divergence of this vector function, which is represented by this expression, we have found divergence of this vector function by dot product of del and vector function. Dot product of this del and this is vector function. This is del, this is vector function, and dot product will be used, carried out to find divergence. So this has been extended in this expression, and we found the final expression as 2z plus 7. So for a general point, we can say this divergence of function x comma y comma z is equal to 2z plus 7 at point x comma y comma z. At general point, 2z plus 7 is divergence of function at point, general point. Let's take a specific point 1 comma 3 comma 7. Put the value in this general point, that is 2 into 7 plus 7, 21. So divergence of this function at point 1 comma 3 comma 7 is 21. So that is how we find divergence of a function, vector function. So and then it will come in the form of divergence for general point x comma y comma z at a particular point, and to find at a specific point, put the value of that coordinate in general expression of divergence, that is 2z plus 7 for this function. So divergence is 21. So at this point, so when you will change the points, you will find different values of divergence. So that is the definition of divergence. Now we will discuss the physical interpretation of divergence. So divergence, as its name suggests, as the name of divergence is given, it's a divergence. It's the property of a vector function to diverge, to expand. How at a particular point we have found a divergence at a particular point? It can be calculated for a particular point. So that value of divergence shows whether the function is expanding or function is converging, how it is diverging at a particular point. So just for example, let this is a box, it's a sphere, and center of the sphere you have a pipe, simple pipe of water. Now we are discussing physical interpretation of divergence. This water is flowing, it comes in the center of the sphere, and in the periphery of the sphere there are holes. So water will come out like this from this sphere. So you can say at this point water is diverging. That is the meaning of divergence. Water is diverging. It is going outside. So at this point divergence is positive. Just remember, when at a point the vector function diverges outward from that point, outward, then divergence is positive. And when at a particular point vector field is converging to that point, then divergence is called negative. So this sphere, we have taken for example this sphere, water is coming from here. So when it goes in the center, it comes out from this sphere. So water is coming out from the sphere. So we can say the divergence, that is for divergence for what? We have discussed divergence for a vector function. So here vector function is velocity of water. Velocity is a vector function. So you can see velocity is different at different points, and here it will be different, and it will come out with some other value. So there is a vector function, that is velocity, and if we found the divergence of velocity, so at the center this velocity is radially outward from the sphere. So divergence of velocity vector field, divergence of velocity vector field is positive at this point because it is diverging outward, radially outward from here. Second, when the divergence will be negative, just take this sphere, make the hole in this sphere, connect a pipe at the center, and let the sphere is submerged in water, and a vacuum is created. Vacuum is created in this pipe. So the sphere is under vacuum. So this water surrounding the sphere will enter from outside inside the sphere. This sphere is a hollow sphere, and the sphere is under vacuum. It is submerged in water. So due to vacuum, it will suck the water. So water will come inside this sphere radially inward. So the velocity vector, velocity field will be converging at the center of the sphere. So we will say the divergence of velocity in this case is negative, and divergence in this case is positive. When it is expanding, it is going radially outward, divergence is positive. When it is coming radially inward, it is collapsing, then divergence is negative. So that is the physical interpretation of divergence. Divergence at a point for a vector field is property of that field which represents how this vector field is expanding or collapsing at that point. That's it. That's the divergence. So we can also say for a positive charge plus Q, electric field, it will create an electric field. Electric field will be radially outward. We have earlier represented electric field by a positive charge in terms of field as a vector function. We have represented in earlier example earlier in the definition of field. So this field, electric field, is expanding, going radially outward. Electric field around this charge is going outward. So the divergence is positive. Divergence, when you will calculate the divergence which we have calculated at a point, then you will get a positive divergence. Similarly, for negative charge, minus Q, at all these points, electric field is towards this negative charge. So field is collapsing at this point. So for this electric field created due to this negative charge, when you will find divergence of that electric field at this point, that divergence will come negative. The negative sign of divergence indicates divergence, the field is collapsing, and positive sign of divergence at a point indicates at that point field is expanding. That is the physical interpretation of divergence. The third operation is called curl. We have used del operator to find gradient of a scalar function which generates a vector function, vector field. Then we found divergence by using del operator, and in that case vector field is converted into scalar field, that is opposite to gradient. Opposite to gradient, divergence in gradient, scalar field is converted into vector field, whereas in divergence, the vector field is converted into scalar field. Both these operations are example of illustration of del operator. How we use del operator to find divergence? We use dot product of vectors. Similarly, curl. Third operation is curl of a field. So curl is nothing but curl for a vector field. This is also found for vector field like divergence. Divergence is also we find divergence for vector field. Similarly, curl is also found for vector field. Whereas in curl we use cross product. Unlike divergence, where we use dot product. In divergence we were using dot product. In curl of f, curl of vector field x, y, z. Curl of vector field x, y, z is represented as del cross vector function. So divergence we have used dot product, and in curl we use cross product. So first we will find how to find curl at a point for a vector field, and then we will discuss the physical interpretation of curl. So for example, there is a vector field, a simple, we will just take any arbitrary vector field x square I plus yj plus zq k. This is a vector field. Now curl, we want to find curl of this vector field x, y, z. So curl of this vector field is nothing but cross product of del with field x, y, z. So that is del x I, that is expression for del z a plus del z k cross fx y z we will put this expression x square I plus yj plus zq k. This can be written as I j k del del x del del y del del z. From definition of cross product which we have discussed in vector chapter, we can find cross product of del and vector field with this determinant. Coefficient of I is x square, coefficient of y is y, j is y, coefficient of k is z. So this will be I del del y of del y of zq minus del z of del z of y into y plus del y of zq del z of plus minus j del x of zq minus del z of x square del z of x square plus k del x of y del x of y minus del y of x square del y of x square. This is how we will find the curve with the simple formula of determinant I del y of zq minus del z of y minus j del x of zq minus del z of x square plus k del x of y minus del y of. So you see these all terms are 0. So this is a 0 vector. So we can say curl of this function for a general point x comma y comma z is 0. So when we got 0 curl at a point or for a general point, when a curl of a function is vector field is 0, this is called a irrotational field. The name is irrotational field, that is curl is 0. So here we got 0 curl, that means this given field is irrotational field. Similarly, if we find some finite value of curl, then that is called a rotational field. Again I will repeat, when we find curl as a 0 for a given vector field, then that vector field is called irrotational. When there is some finite value of curl for a vector field, then that vector field is called rotational vector field. So for example, we are changing it. So let this field was xy. Just xy. We found a new field. We are finding curl for a new field fx comma y comma z. Earlier that was x square I plus yj plus zq, for which curl was 0. Now we have slightly changed the field x square I plus xyj. Instead of yj, we have put another variable xyj plus zqk. Now we will find curl. In this case, this curl will not be 0. So let us find the curl of this vector. curl of this vector is I J K del x del y del z x square x y z. So we will not repeat that all expression again. That is a curl. So curl of function x y z is given by y. This is y at point x comma y comma z. At general point, curl of this field x y z, which we have changed from earlier field, is yk at point x comma y comma z. So let point for a specific point, as we are finding operation for a specific field also. So let's just select an arbitrary field 4, 5, 8. For this field, y is 5. So curl f is 5k at point 4, 5, 8. Curl of this vector field is 5k. So you can see this vector is a vector, and curl, unlike divergence, whereas divergence was a pure number because that was a dot product. Unlike divergence, curl is a vector quantity. So curl, we find a vector quantity from a given vector field. This was a vector field. We found curl of this vector field, and curl is also a vector field. It is vector field for general point x comma y comma z curl, and this is curl for specific point 4, 5, 8. So curl is a vector, unlike divergence. Divergence is a pure number because that was dot product, and curl is a vector. So now we will understand the physical interpretation of curl. So here it has some finite value which we were discussing. For earlier function we found curl 0. So when we find curl 0 for a given vector field, that vector field is called irrotational vector field. Here for this new field which we have changed, we found curl as 5k, or for general point it was y into k. That is non-zero. Curl is not 0 at any point except z is y equal to 0. So for a non-zero curl, it is called a rotational vector field. Rotational vector field. When curl is non-zero, vector field is rotational. When curl is 0, vector field is irrotational. That is interpretation of curl. Now we will find what is actually meaning of curl. So as the name of curl suggests, like divergence, that was property of vector field to diverge or collapse. Similarly, curl is a property of a vector field which its name suggests, curl, to rotate. It's a property of vector field to rotate actually. So just for example, when we find curl at a point, so this is a three-dimensional coordinate system. Let at this point we have found some value of curl. Value of curl means there will be a vector. Curl is a vector. So curl is a vector. So put a small ball. Curl is a microscopic property. First remember, curl of a field is a microscopic property. Unlike many of us will think that it's a macroscopic property. It's property to rotate something. It's a property of to rotate something. Whereas Actually, curl is a microscopic property because it is defined at a point. Curl is always defined for a point, which we have found for a specific point curl. Earlier we have found the curl for a specific point. So for a point, just put a imaginary ball at that point where we are finding curl. And if this is curl is if curl is 0, this ball will not rotate. This ball will not rotate due to vector field. When curl is non-zero, the vector field around this ball will be like this. Vector field, that these small arrows are representing vector field, direction of vector field. So at this point, if it is non-zero, curl is non-zero, the vector field will be like this. It will create a small whirl. So for a non-zero curl, this vector field, let this vector field is rotating this ball, and this ball will start rotating. So this ball will have two things. One, magnitude of rotation. Second, direction of rotation. So magnitude of rotation is magnitude of curl vector. If it is rotating fast, then magnitude of this curl vector will be high. Higher the magnitude of curl vector for a vector field, higher will be the tendency of field to rotate at that point. And direction of this curl vector, as we know, cross product is perpendicular to cross vector field, is a perpendicular to both vector field which are being cross multiplied. So direction of this curl vector field, curl vector, the direction will decide the rotating direction of this ball, that is clockwise or anti-clockwise. Generally anti-clockwise direction is assumed coming out from the board, and clockwise direction is assumed going inward in the plane. That is the convention. So curl vector, if it will come out of the direction of curl vector is such that it is coming out from this plane, it will rotate in anti-clockwise direction. It is going in the plane, it is rotating clockwise direction. So the magnitude and the direction of this curl vector decides the magnitude of this rotating field, rotation of field, and direction of this curl vector will decide the direction of rotation. So that is the physical interpretation of curl. As the name suggests, curl means rotate, rotate around some axis. So again I will repeat all these three operators. First was grad of function x, y, z. Here this function is scalar function. So this is a vector field. Second is divergence of function. Here this function is vector. So this grad is also written as del f x y z. Divergence of function is written as del dot this vector function, and this is a scalar quantity. And third is curl f x y z is equal to del cross. Here also this field is vector field. Function, vector function f x y z and this is a vector function. Curl is a vector function, divergence is a scalar function, and grad is also a vector field. So they have their own meanings, their own interpretations. So I think this much is sufficient at this level, and you need not to go much detail of these concepts, because only superficial understanding of these concepts are required to understand theorems like Gauss and Ampere and basics of vector calculus, which is necessary at higher secondary level. So you will study all these things in detail in higher mathematics and graduate level. So these are the basic terminologies which are used in vector calculus. Curl, that is a tendency of the vector field to rotate simply. Tendency of the vector field to rotate, that is curl. If curl is 0, then field is called irrotational. If there is finite value of curl of a field, then it is a rotational field. Similarly, divergence is a property of a vector field to diverge. If divergence at a point is positive, then means the field is diverging, expanding, and if divergence at a point is negative, that means the field is collapsing.